What up, everybody? Today we're going to be showing you how to make this really cool spreadsheet where you show different musical tunings with some harmonic information, update one field, and all numbers will follow. Really cool stuff. But first, some background for my non-musicians in the crowd. If you were to take a music class right now, and it doesn't matter what instrument you decide to play, could be guitar, trumpet, piano, they're going to make you tune to 440. If you buy a tuner at a music store, if you use recording software, that's just the standard. Now, I hope you've seen a piano before, and if you have, you'll know that there's 12 notes that repeat, and every time those 12 notes repeat, they call it an octave because typically a scale will have 8 notes, even though there's 12 total, called a chromatic scale, but they call them octaves, so just bear with me here. The way music works in terms of frequency, though, is whenever you have a note, if you go to the octave below, it's 220 versus 440, that's a half. If you go an octave above, 440 versus 880, that's a double. So it's all about halves and doubles here. It's a logarithmic scale, and that's what this chart shows. So if we go back to 440, you'll notice that all of our A's are halves and doubles. And that's the vertical axis here. And the horizontal axis, you will see the harmonic information. And this is where it gets really fun and interesting. What harmonics are is essentially that same number. It's a multiple of that same number. So 55 plus 55 is 110, plus 55, 165, plus 55 is 220. So it's that same number added by itself over and over again versus halves and doubles. And these two mathematical formulas coincide with each other to create harmony, to create sound that's pleasing to the ear. And there's a lot of theories of different tunings to use, but today we're going to stick with just the equal temperament scale, which divides our 12 notes into equal segments. The higher you go up, the more space you get between them, but that's how that works. And I think they even show a cool little chart right there. Yeah, music is logarithmic. Okay, so a little bit more background as well. I got into this whole thing. If you've seen some of my previous videos, we've talked about it before. There was an online conspiracy about 440 hertz that supposedly in the 1900s that the Nazis decided to change the standard to 440 hertz because it makes people more docile, more obedient. I'm not sure if any of that's true, just passing information along. A lot of people have done experiments with Chladni plates and cymatics. These shapes right here that you see are... it's water, and they'll do experiments where they shoot certain sound waves at a bowl of water, and it'll create these different beautiful shapes, whereas other shapes are more chaotic. And so there's a lot of things to consider when you do that, though. There's, the size of the bowl, the minerals in the water, the temperature in the room, the shape of the bowl, a lot of things to consider. So kudos to anybody doing research on that. That stuff's fun. Same thing with Chladni plates. What they do is they get these metal plates and they put sand on them, and certain frequencies will have very beautiful shapes. Other frequencies will just be kind of jumbles of sand, and a lot of research going on in this field. Very cool stuff. So that's how I got into it, and I wanted to see, okay, well, I needed more information, more of an insight into, well, what happens? What's the difference between 440 versus 432? What if I want to tune to 444? What if I want to tune to 448? How does this all work? So I created this chart here to help me decipher all this, and I'll be showing you how to make it. For those of you that don't have time to follow along, completely understand, don't worry. I will be putting the finished version in the description. So now let's go ahead and jump into our sound design software, and let's get into harmonics for those who don't know. Now, whenever you play a real musical instrument like a piano or an acoustic guitar or woodwind or brass, they're going to play complex waves. So for example, let me see. Let me just pull up a piano real quick, and let's just go to sounds. I'll just pull up any sound here, and let me show you what that looks like. So if we get a complex wave here and we pull up our spectrum analyzer, let's go ahead and put the spectrum analyzer there. You'll see all kinds of squiggly lines, and this is called a complex wave. But in order to kind of break this information down and make it a little bit more digestible, we're going to be using just synthesis. So these are all synthesized waves. You have sine waves, saw waves, square waves, triangle waves. They are not possible in nature alone. They are created electronically, and that's why they call it synthesis. So a sine wave is a rounded wave. It's said to be the most purest of tones. It has no harmonic information. Saw waves have more harmonic information, square waves and triangles as well, and we'll get into that right now. But I want to mention something really quick. If you, in fact, get a sine wave, and let's go ahead and play it here. This is a 100 hertz sine wave, and you'll see it on the chart right there as a 100 hertz sine wave. There's no such thing as a completely pure tone. Every single device that you play out of a plug-in, a computer, an amplifier is going to have what's called harmonic distortion. And if you notice, when the note first plays, you'll see all these extra squiggly lines. Well, wait a minute, I thought this was a pure tone with no harmonics. This extra information here is what's called total harmonic distortion, and this is what manufacturers of amplifiers and plugins use to determine how good their device is. So it's said that the less harmonic distortion that a device has, the better it sounds, the more expensive it is. And so just good to keep note of that. But I want you to notice here, a pure 100 hertz sine wave, as close as you can get, you still have these little peaks here. And where are they occurring? Well, 100 hertz wave, you got a little peak at 200 hertz, 300 hertz, 400 hertz, 500 hertz, 600, all the way up. Now that is what this line of the chart is showing, and this is why I did this here, so we can just change one number, one field, and we get all the information we need. 100 hertz tone has harmonic information at 200, 300, 400, 500, 600. And we have even order harmonics, and we have odd order harmonics. And there's an interesting doubling and halving that occurs as well, and that's where you'll see that's what this color information is showing you, is that the double and a half, you just can't get away from it. It's going to be there no matter what, even in the blues here. Interesting. 5, 10. Good stuff. Anyways, so a sine wave, as you can see, is round, and it's as pure tone as you can get, like a circle. And if we were to actually look at it in terms of audio, let's go ahead and zoom in all the way. Let me go into the beginning here, and let's zoom in as close as we can. It's round. Interesting. Well, what about a square wave? Let me go ahead and get a square wave here, and we're going to turn this into audio. It's square. Interesting. Well, what's the difference? Well, that's what I like about Ableton here. You can break it down into a full-on square wave, or you can do a more slimmed-down version. So let's start with the square 3. That means that there's going to be 3 harmonic tones added to a basic square structure. So let's play that. This is what it sounds like. And you notice there's our 3 tones, and they're occurring at 100, 300, and 500. So it's skipping 200, 400. In other words, it's skipping our even ordered harmonics. So a square wave is said to be composed of all odd order harmonics. And we can go ahead and we can do 4, we can do 6, we can do 8, all the way up to a full square wave. And you'll notice in all of those cases, it skips the evens. And that's a square wave. Same thing can be said about a triangle wave. Let's go ahead and take a look at it here. Sounds very similar, but a little bit different. But it exhibits the same phenomenon here, where they skip the even order harmonics. And you guessed it, if we freeze it, flatten it, and zoom it in, it's a triangle. That's why they named it that. Now, the grand mamma jamma of them all, dubstep fans love their saw waves. They love their saw waves, like electronic music, dance, dubstep, all that good stuff. The saw wave is very rich in harmonic information, and can you guess why? It's because there's our even order harmonics. That's your 200, your 400. So saw waves are great because they include that extra harmonic information, and they sound more rich in that sense. And so that's what this chart is here. Gives you a full-on breakdown of the harmonic information for synthesized waves, not complex waves. If you look at a piano, it's going to be different. If you look at a guitar, it's going to be different. But you can use these principles and take derivative information from it. And one more thing, let's go ahead and look at our saw wave. There it is. Looks like a saw blade. Now, this is a down saw. If we reverse it, let's go ahead and reverse it. This is called an up saw. It sounds very similar. All right. Nice. And that is how synthesis works. And, people do cool things, like they'll get they'll get an EQ filter or something like that, and they use saw waves, and you can do a lot of cool stuff with that. So, triangle and square waves are typically used for like bass instruments because there's less harmonic information, there's less clutter in the lower frequencies, and then they'll typically use like saw waves for more melodic instruments in the higher frequencies. And so a lot of this stuff is how electronic music works. But let's get down to it, and let me show you how to make this chart real quick. We're going to go ahead and we're going to show you from scratch. All right, so let's go ahead and jump into Google Sheets. We'll create a new spreadsheet here. And all this information will also apply in Excel if you prefer to use that. But hey, Google Sheets is free. Why not, right? And I'm going to just copy this information from the previous file, just because I would hate for y'all to have to watch me do that from scratch. What it is just white keys and black keys here so that you can reference a piano. And I left some visual indicators to easily find information as quick as you need. Interestingly enough, because of the way that the piano is laid out, octaves begin on the C note and not the A, even though A is the first letter and we tune to the A. But hey, hate the game, not the player. I didn't come up with the rules, right? So what I'm going to do here is I'm just going to move these over to the center just to have a little bit more of visual indicators of where we're looking, because A is the note that we're going to reference the most. So A1 is the field that we will change to alter the tuning. So let's go A1 to alter tuning. And A1 is our middle A. Oh, this gets confusing real quick, right? Field A1 references our middle A note. And so what we do is we're going to hit equals and A1. There we go. So now anytime I change field A1, it will change that field as well. All right. Let's see. 432. Cool. It's working. All right, step 2 is we're going to need to get our formula. And in this case, I'll be using equal temperament tuning. In the West, we use 12 notes, as we mentioned before. In certain places in the East and other parts of the world, they'll use different divisions. So they'll do, a scale with a division of 9, or scale with a division of 24, or different type of, I believe they call them microtonal tunings. And that stuff's really interesting. It gets really, really fun real quick. But let's just stick to the 12 for now. This is called equal temperament. And there are different types of tunings as well. There's back in the day, before calculators and the BC times, Pythagoras and all that stuff, they try to use whole numbers as much as they could, or fractions, because they didn't like decimals. So just temperament and Pythagorean tuning, they will have more whole numbers because they didn't like using all these decimals. But hey, we got calculators nowadays, so why not? Now, here is step 3, and this is the true power of Excel and Sheets. You create a formula with the equal sign, and if you use the dollar sign, you can create a sequenced formula, which is super cool, and you'll see how that works right now. So I'm going to go ahead and reference B62, which is your yellow, and you'll see that C1, our formula right here, is being referenced as the purple, and I'm going to hit enter. Now there's our tuning for this note. Now I'm going to hit copy. I'm going to select all the fields that I want. I'm going to paste, and there it is. Super fast, super quick. There's all our tunings. But look at all those decimals. So equal temperament has a lot of decimals. Just temperament will be less, and Pythagorean will use fractions and stuff like that. So keep that in mind. This is just one way to do this. But you'll notice I only did the notes below our 440 because those require you to divide the formula. Anything above 440 will require us to do the multiplication. So let's go ahead and do B62 times our formula on field C1. There we go. Copy that. Select our fields. shift click, paste. And there's our tuning. Beautiful. Now, this is called the fundamental note. Fundamental. And this is technically our first harmonic. Now we want to calculate our second, third, fourth, fifth, sixth, seventh, eighth, ninth. Let's go to 10. You can go as high as you like. As you saw on the Ableton session earlier, you can have as many harmonics as you wish. You know, let's go ahead and add 2 more, just so we can see the information there. So we go all the way to field N, and we're gonna go all the way down to, let's see here, 112. So 112N. All right, and we're gonna apply our formula on all of this. Now check this out. We're going to reference our fundamental here. That's on field B5. So let's go ahead and do $$B5. And we're going to multiply that by our second harmonic, 2, which is going to be in field D, $1. There it is. So D1. Okay. There it is. We'll go ahead and we'll copy that. And let me go ahead and drag that over to all of our fields. There it is. Cool. And even more fun than that, let's go down all the way to 112. What was it? N112, and paste. There it is. There's all our information. Super quick. From there, you can go ahead and you know, select all your A's. Do whatever you need. At this point, this is where you can customize it for your own needs. I like to be able to reference my information really quick. So we'll select all of our A's. We'll bold them all. That way we know. Maybe we'll, you know, make it a slightly larger font than the rest so that we know, oh, okay, there's our A. You can do kind of how I did in the other one here, where you can color code things. Maybe you want to color code your odd and evens, so we'll color code our evens good right there. We'll color code our odds. It's entirely customizable. It's up to you how you want to do it. You'll notice in the original sheet that I made, I have these additional little pieces of information, and this is pretty cool to use if you're ever mixing or doing some EQing. Let me show you what this means real quick. So we're referencing our C0. Our second harmonic is going to be the same note as C1. So 32.7, 32.7. Our third harmonic is going to approximate G1. So if we go G1 is 49, 49.05. So that's why I put the little tilde there. And this is why even order harmonics sound so good, is because they are essentially octaves, and you're just doubling up that information. You're making it sound thicker. On the other flip side, the odd order harmonics typically will sound good as long as you're using major, because if you notice the fifth note here, the fifth harmonic is, let's see, 81.76. So if we go down 81.76, that's real close to E2, which is a major third, 2 octaves up. And so if you're playing a song in major, awesome. Maybe you boost this frequency. But say you're playing a song in minor. Well, you don't necessarily want a major note to creep into your minor song. And so this will give you an indicator that, like, well, maybe dip that frequency right there. You're getting some major harmonic information in a song that's supposed to be minor. Same thing with like your seventh order harmonic right here. You get like a microtonal thing going right here, where 114.46, it's not quite A sharp, not quite A, somewhere in between. And so maybe you dip, you know, you do an EQ dip on that one. And so this is the power of all this information, and you can customize this in however fashion that you would like. And like I said, feel free to, if you didn't get a chance to follow along, I will have all of this in the description. And one last little thing here. If you'd like, we can go another step further. I can make another video about how temperature and wavelength and cycles per millisecond and speed of sound, all of this influences each other. This is the power of Excel. This is the power of these spreadsheets. Humanity hasn't had this much power mathematically in our hands in a long time, and it's amazing. And you got to use it, man, to have this much knowledge and power and not use it, not spread it, it's a shame, so please use it. For example, right here we got all of this information showing how the speed of sound is affecting, how temperature affects speed of sound, how speed of sound affects wavelength, how wavelength affects cycles per millisecond, and you also have your handy dandy tuning changer right there, just like in the other one. So hey, if you like this video, we can make more. Thank you all. Like and subscribe, and don't forget to hit the bell.